Welcome. So, we are in the module 7. So, we are discussing the solution of boundary value problems and we are considering the problems in Flexure. So, in the last class we have discussed the pure bending of a curved bar essentially, and then we found out that the normal stress sigma theta theta we are considering in the polar coordinate system. So, normal stress is essentially quite good with the hyperbolic form of the stress what we obtain from the strength of material approach. Now, in doing so we have also used the stress function approach. In the stress function approach, we assume that our stress function is a function of r only. There is no theta here. So, there is no theta here, and this leads to our normal stresses are of this form. So, sigma theta theta is of this form and sigma r r is also in this form, and sigma r theta, which is a requirement for the pure bending, is also 0. So, now what we did, we use the three boundary conditions that we have seen, that is here in the radial convex side there is no normal force, and the this side there is no these two sides there is also no force generated, only couple acted, and sigma r theta there is no tangential force. So, sigma r theta is 0. With these three boundary condition, we could find out sigma r r, sigma theta theta, and sigma r theta equals to 0 is already satisfied. So, with this sigma r r and sigma theta theta. So, this sigma theta theta what we calculate with the strength of material solution via Winkler-Black formula. Now, our present objective is to find out what are the displacements, as we did it for the rectangular or the straight case. We found out from stress to displacement. So, you see, as we have seen earlier that these sigma r r and sigma theta theta and sigma r theta, this does not depend on the material. So, this beam now can be made of any material. So, when we try to find out the displacement, then we need to invoke the material laws or material constitutive behavior. Then the material parameters comes into picture. So, for a specific material, the material parameter values take specific values. So, we will be again considering the isotropic linear elastic material. For which the stresses and strains we know in the linear regime or linear elastic regime, which follows by the Hooke's law. So, now we are doing it in the polar coordinate system, for which epsilon r r is essentially del u del r, which is 1 by E sigma r r minus nu into sigma theta theta, and epsilon theta theta is u by r plus 1 by r dv d theta. So, this also equals to this, and then shear strain in r theta system is gamma r theta, which is this, which is equals to the shear modulus and this. Now, if I just substitute our stress expression that we have got from the stress function, and then if I write it, if I compute epsilon r r, which is du by dr, which looks like this. Now, after integration, simple integration, if I integrate this equation, I get the expression for u. And since u is a function of r and theta, u is a function of r and theta. So, here u is a function of r and theta, and v is also a function of r and theta. So, we are integrating with respect to r. So, then the integration constant will be a function of theta, right. So, this gives us the first expression for the u, and similarly if I substitute this u here, and then if I substitute the stresses sigma theta theta, sigma r r from the previous approximation, I can now calculate this dv d theta. So, if I write it in a little proper manner, like this dv d theta will be your r epsilon theta theta minus u by r. So, or minus u. So, if you look carefully that we have just used this equation. So, now epsilon theta theta I can substitute r by e is essentially sigma theta theta minus nu sigma r r minus u. So, this is my dv d theta. So, in this expression I know u from here, right, and sigma theta theta we know and sigma r r we know. So, if I integrate this equation now I can get the v. So, now let us do that thing and check what happens. So, essentially this is the case. So, dv d theta is r epsilon theta theta minus u. So, and r epsilon theta theta is essentially this quantity. So, if I substitute and after doing some manipulation which I have obviously not shown here, so you can do this manipulation and this becomes dv d theta becomes this, which involves only one constant which is b, and this f theta. So, f theta is coming from the u solution of u in the previous slide. So, now this dv d theta if I integrate, so it becomes 4 b r theta by e minus integral of f theta d theta plus g r. Now, see v is also a function of r and theta. So, and we are integrating with respect to r and then with respect to theta. So, the integration constant will be with respect to r, which is a function of which is a g function of r. Now, what we have? We have v and we have also u from the last slide. So, if we substitute gamma r theta, that is del u by del theta and dv by dr minus v by r, which is essentially the shear strain in our theta system, and then this shear strain is essentially the shear stress by the shear modulus g. Now, if you remember for pure bending case, the shear stress, this sigma r theta is essentially 0. So, then this implies that shear strain will be 0. Now, if I substitute u and v and then equate it to 0, this will be my final equation. So, as we did it for the straight case or the straight beam, that these some of these will be function of theta, some of these will be function of r only, and some of these two sum of function of r plus sum of function of theta will be equals to 0. This is same thing, and if I use now gr equals to fr and f theta equals to h sin theta plus k cos theta, where again f, h and k are constants, we need to find out. So, this satisfies this equation, right. So, you can just substitute and check whether this satisfies or not. So, now this with these functions of this form fr and f theta and gr, we can write now u and v. So, u becomes this, so this is u, and then this is f theta. So, f theta is h sin theta plus k cos theta, and v becomes this plus integral f theta d theta. So, which is h cos theta minus k sin theta, and fr, which is gr. Now, here if you look carefully, that already we have found out a, b, c. So, these three constants we have already found out from the stress boundary condition. So, this even though I have written it here, so these constants we know. So, we have to find out only three constants, which is h, k and f. So, only three constants if I can find out, we can find out displacements u and v. So, let us see how we can find out these three constants. So, to do that, we have to again use the boundary conditions in terms of displacements. So, what in the boundary conditions we can in the radial direction, that means that the centroidal axis. So, this is the radial direction. In this radial direction, we can fix this point. So, at this point we can fix this point. So, this point at u and v will be 0, and dv dr, that means the a vertical line along this fiber, vertical element will be essentially fixed. So, it prevents the rotation of the vertical element on this point. So, which is implied by dv dr equals to 0. So, at theta equals to 0. Remember that theta is measured from here. So, theta is this. So, this is theta. So, now at theta equals to 0, r equals to r0, r0 is a plus b by 2. So, this is a and this is b. So, this is a plus b by 2. So, now this if we invoke into the k, that is the u and v, then we can see that if I invoke this first two condition and then dv dr, then we can get f equals to 0, h equals to 0, then k is non-zero, which is of this form. So, now if we write v, which is v here, which is only k will be non-zero. So, v looks of this form. So, what is v? If you look carefully, that v is the fiber vertical axis, the displacement. So, now if you see that this v represents, actually there is a translation here, which is a k sin theta, and there is a rotation which is 4 br by e, 4 b theta by e. So, these rotations and these things allows these fibers to be remain plane after bending. So, this is actually the condition of pure bending that we use. So, this also proves that this is a solution of a pure bending, where we assume that fibers remain plane before bending and after bending. So, this equation actually says or verifies this. So, so this actually is a displacement for the pure bending case. So, similarly with f and h and k, we can find out u also. So, this completes the pure bending part. what we are discussing, what we have started discussing in the last class. So, here what we have done in case of a pure bending, we found out the stresses, and then from those stresses we to find out those stresses we have used stress functions. The stress functions are a function of R only, and these stress functions involve some constants, and those constants we found out stress boundary condition. Now, once we have done with the stresses, then we found out the displacements, and those displacements are essentially from the stress strain relation, wherein we invoke the material laws, which is essentially Hooke's law, and then with this Hooke's law we find out the displacements u and v using the displacement boundary conditions. So, this is the complete solution of the pure bending problem of a curved bar. Now, in the next, what we have planned is the 2D cantilever beam, which is a 1/4 of a circle, and this cantilever beam is essentially fixed at this end, and then there is a force or the shearing force resultant along this line, which is P. Now, this is similar to the cantilever problem that we have solved in the rectangular means straight case. So, this problem will also try to address here. So, this problem, if you remember that you have already solved this problem via strength of material approach, and you know the solution for this. For instance, the displacement here at the tip of the cantilever, you know that what is the formula. So, we will see whether this formula actually works here or not. So, now the boundary condition for this, so we will follow usual theory of elasticity approach, where we need to have the boundary conditions. The boundary conditions are sigma r theta r equals to a and r equals to b is 0. So, these are there is no shearing stress along these part. So, at the free these two part. So, r equals to a is this and r equals to b is actually this, r equals to b is this. So, there is nothing, so sigma r theta, so there is no force here. So, these are free, and sigma r is actually r equals to a and b, it is 0. So, there is also no normal force, there is no tangential force also, and p, the load here is essentially sigma r theta d r, and we have likewise in the previous case we have taken it is 1. So, for theta equals to 0. Remember, this is only for theta equals to 0. So, theta is measured from here. So, this is theta. So, now this if you remember strength of material solution, this bending moment is varies with sin theta, right, if you remember the strength of material solution. So, bending moment at any cross section of that curved beam varies with the sin theta. So, this fact will use while approximating the stress function. So, the stress function is essentially here, this is B and this is the cross section. So, here let us assume the stress function is f of r sin theta of form. So, this stress function is motivated from the strength of material intuition, where the bending moment varies at in a cross section is with the sin theta, and it is Fr is the that we have seen in the previous case. So, our phi is not only dependent here on r, it is dependent on theta also. So, Fr sin theta. Now, if we substitute this, so our biharmonic equation will be full equation here. So, these terms are there which were not there in the previous case. So, this biharmonic equation, if I substitute this quantity, so you will see that this becomes sine squared theta, and so this goes there will be sine squared theta here. So, this sine squared theta 0 means theta is equals to 0, which is a trivial case here. So, this quantity has to be 0. So, this is again you see this differential equation is very similar to the previous case, only these terms are extra. So, now, this differential equation again with the substitution of t equals to e to the power r, we can do a linear differential equation with constant coefficient, and solution of that differential equation is of this form. So, you can also again like in the previous case, you can also check whether this function f r satisfies this differential equation or not. So, we are not discussing this here. Rather we are interested what it produces here. So, this f r is actually the involving 4 constant a, b, c, d. So, this is also another constant a, b, c, d. So, these 4 constants again we have to find out from the stress boundary conditions which we have discussed in the previous slide. So, now let us see how this 4 constant produces stresses. So, for this, so my phi becomes this. So, my phi becomes this. So, which is a function of r and theta, even though this functions looks this function looks very simple because we have used separation of variable so f of r into g of theta kind of thing, and g of theta is essentially sine theta. So, sigma rr we can compute, and sigma theta theta again we can compute, and sigma r theta we can compute. So, sigma rr if we compute from this phi, which is the stress function phi is of this form. So, the sigma rr is of this form which involves a, b and d, 3 constants, and similarly sigma theta theta which is del square phi by del r square which also involves a, b and d. Now, contrary to the previous case, the sigma r theta is not now 0. So, this is because phi is a function of r and theta also. So, this quantity is non-zero, and then this quantity becomes this. So, you see all stress components are involved in 3 constants a, b and d. So, we need to find out these constants a, b and d with the stress boundary conditions. So, let us see how we can find out the stress boundary conditions, these constants. So, the first boundary conditions is essentially the sigma r theta, r equals to a and r equals to b. There is no tangential forces along these lines along the radial boundary, and sigma rr, that is there is no normal forces, is 0. So, if I just put these 2 conditions, so essentially we substitute in the previous stress expressions, and then this stress expression becomes this. So, we substitute r equals to a and r equals to b. So, we get this. Now, the third condition, that is the at theta equals to 0, this stress resultant becomes p. So, sigma r theta integral sigma r theta dr from a to b. So, from a to b here this becomes p at theta equals to 0. So, sigma r theta is this. So, essentially del r by 1 by r into d phi dr, which is sigma r theta, and this if you integrate, then again this quantity will be from a to b. So this is my this thing, and then if I substitute d phi d theta and divide it by r, then I get the this quantity which is this, and this is equals to so minus actually I have interchanged the limits. So from a to b I did the b to a because it is a minus. So this becomes this. Now if I substitute now b and a here, so this is my final form of the equation where which I need to solve. So I have 3 equations, 3 unknowns. Again, like in the previous case, I have 3 equations, 3 unknowns. So what are those? So this is 1, this is 2, and this is 3. So we can find out these 3 unknowns. So and finally compute the stresses. So with this we can find out. So this is my first third equation essentially, and this is my first equation, and this is my second equation. So we got these equations from the boundary conditions, that is obtained from the boundary conditions obtained from the stress boundary condition. So if we solve these 3 equations, we get A of this form. Again there is an n, so n is essentially composed of A and B, and then B is P a square B square by 2n, and D is P into a square plus B square by n. So here once we know A, B and D, we can compute all stresses like is in the previous case. So if you now look carefully, what are the stresses at the 2 ends of the beam? So if you look theta equals to 0, that is at the upper end of the beam, if you look, then at this upper end actually this sigma theta theta will be 0. So sigma theta theta will be 0. So that means these along these lines the normal stress along these lines will be 0, or this will be 0, but sigma r theta, so r theta which is the along this, so this will be non-zero, which is your p by n 3r a square by b square r cube minus a square plus b square r. So which is involving all those constants a, b and d, and n is essentially the same thing here what we have seen. And so now see in the lower end, on the contrary, in the lower end where theta equals to pi by 2 is only the normal stress exists. So this normal stress exists, but shear stress is 0. So this can be easily verified from the stress expression that we have obtained. So if you look carefully in the previous slides, so that the stress expression, you see for the theta equals to pi by 2, this this normal stress is actually this is in terms of cos theta. So this actually sigma r theta will be 0 because it involves cos theta. So but sigma theta theta, which involves sin theta, will be non-zero, but at theta equals to 0 the situation is just reversed. Sigma theta theta equals to 0 and sigma r theta is non-zero. So basically likewise for the straight case, the cantilever case, we have also found out here the stresses compared to the stresses via approximating the stress function, or specifically the solving the biharmonic equation. Now, while approximating the stress function here, we used our intuitive knowledge of strength of material, where the stress function is function of essentially we use the separation of variable, where the phi is a function of r theta can be written as f of r sin theta. So, you can use instead of sin theta, you can use cos theta also. If there is a couple, you can use cos theta, so which will give you the solution. In this manner, I would suggest you to consult the book I have suggested in the previous lectures, that is the Timoshenko and Goodyear, the Theory of Elasticity book. There are several examples are there how such stress functions can be taken, and then how these stress function represents certain type of solution. So, as we discussed in the previous class also. So, how to find out these stress functions? It is not just a there is no specific rule. It depends on the how the stress conditions for a specific problem. So, based on the specific problems, how the stress conditions are, we choose the stress function, and it requires experience as well as your practice. So, now in the next class, what we plan is that likewise in the previous examples, for in case of a straight beam cantilever beam, we will also derive the displacement from these stress expressions with involving the stress boundary, involving the displacement boundary condition, where we also use the Hooke's law for material. So, today I stop here. So, we will meet in the next class. Thank you.